before I tell you that, let me tell you one or two more lines. What happens? Let me first tell you few lines about electromagnetic interest. So classical and quantum. Classical electrodynamics and quantum electrodynamics. What is the difference? Then I come to the okay. So you can keep moderating. This actually helps me because I have no string of nodes or points anywhere, right? Not written any slides on. So you see, let me consider two examples: a boy and a girl. If you are the teenagers, so like you, okay? Now they walk past each other. They look at each other, and कुछ होता है. then they walk away. Then they walk away. This, according to me, is classical interest. So scattering of electrons on the basis of the charges. Okay? However, next time what happens that the boy and they are walking past each other, then one guy gives 11 to the girl. Let me give more respect. So the boy gives 11 to the girl, and so this is quantum interest. In the earlier one, there no such. This is quantum interest. So electromagnetic interaction, two electrons or positrons or electron-positron pairs, they are walking past each other, they get deflected, scattered. This is classical electrodynamics. But now one electron emits a photon, and this photon is absorbed by another electron or positron, but traveling nearby. This is quantum electrodynamics. This is quantum wave of interaction. So this photon is the force carrier of electromagnetic forces. In my village language, I will call it डाकिया डाकिया. आप लोग को जानते नहीं हैं, कोई बात नहीं. These are modern times. Okay, but then you need डाकिया a postman. तो राजस्थानी मूवी आपका था, उसमें आपका डाकिया डाकिया गाना है. तो वो डाकिया था, photon was working as a postman. And this poor guy of my times, he had only one postman, one post office, one postman. Then these big interactions equivalent from town, there are W plus, W minus. What is your name? Archal. Oh, Archal is that you make by churning outside. Yes. So now weak interactions is mediated by, it's little bit richer than the electromagnetic force. It has three dakiyas: W plus, W minus, and G0. It's before you call it G0, it's written as Z0. So these three are the force carriers of weak interaction. This is my Abdul Salam. This Weinberg glass house, Sydney glass house, Steven Weinberg and Abdul Salam. Right? तो अब देखिए, मैं इसके पीछे आपको एक स्टोरी बताऊंगा and you will be feeling thrilled. तो मासलेस इलेक्ट्रोडायनामिक्स होता है, फोटोन का कोई मास नहीं होता है, ऐसा हम मानते हैं. तो उसका काइनेटिक एनर्जी लिख देते हैं -1/4 F². But there was a guy by the name Prokop, Italian scientist. This was year 1936. He thought, if I assume that photon had a mass, so he added one more mass term plus some m² into a u square. This is the mass term, like m² phi square is the mass term of a scalar. So some constant m² is self-coupled, a mu is coupled to a mu, or phi is coupled to phi. So he added a mass term to this massless electrodynamics, and then it would give you massive electrodynamics, where the photon would be massive. It would have mass. Okay? Many people thought this guy was crazy. How can the photon have mass? Because W plus W minus and G0 are exactly the counterparts of a proton for in the weak interaction. They are just, and they are massive, not only massive, very, very massive. Their masses are of the order of 80 G, 83 G. You see, all of them have got Nobel Prize, each one of them. I remember in the year 1983 or 84, I was sitting in a lecture like you at Max Planck Institute in Munich, and there was a speaker by the name Carlo Rubia, and he was giving a lecture, experiment, very leading experimentalist, and he was almost very allusive to the Nobel Committee that these guys were ignoring him and not giving him the Nobel Prize. This. He spoke in between his talk and after his talk. He was very vocal and very critical of the Nobel Committee. This was the month of August or something, but then in October or November they announced the Nobel Prize for the same guy. So he made it to just a couple of months later. So, and this, did he get it for W plus minus? Right? I tell you a similar story about Paul Dirac equation. But before I tell you that, let me tell you one more very fascinating, interesting story. You see, 1 hour is always too short for me. I can talk for many hours. But we work within limits. And assuming that this is not going to be the end of the world, we will have more opportunities to talk. Right? So, what did I want to tell you? Now, Dirac. Yes. So, from maybe I will not have that much time. So, from non-relativistic quantum mechanics to relativistic quantum mechanics. But before we go there, let me tell you stories of young people like you. Around the year, exactly 100 years ago, in the 1920s, Germany was supposed to be the seat of learning, and Groningen was known as the city of noble living, where on each street you find some noble living. See? And this was the time then you see these big guys like David Hilbert and all these guys lived during that time. Those were great times. In physics, now there were two young guys. They talked to each other. You also do it. After your first year or second year or third year, sometime you start writing some dissertation. Then you want to talk to this teacher, that friend, to correct and fabricate some ideas, put them together into a thesis. Right? So, one was Stern and other was Gerlach. The German scientist, Stern Gerlach. So they traveled, one guy was in Frankfurt, another guy traveled from nearby some place, and they sat down, they had some idea. They wanted to study, so you consider an inhomogeneous magnetic field. You consider north and south poles of a magnet, but one pole you lay like a wedge shape, running the same wedge, and one is flat. So if you develop some magnetic field between the two, what you find that the magnetic field inside is inhomogeneous. It's not uniform. Which you grab same time. So it's not uniform. Now, and silver atoms were made to pass through this. So silver atoms, they have 47 electrons. System, so effectively it's a 1 electron system. So it passes through this, and here you put the screen and you observe how many lines you get. So they got 2 lines. But this magnetic moment of the electron is proportional to the orbital angular momentum L. And L has eigenvalues 2, little l plus 1. Little l can take value 0, 1, 2, 3, integer. So 2l plus 1 is always going to be odd. 1, 3, 5, and so on. So for little l equal to 0, 2l plus 1, it has to be 1. So you must observe 1 line. But then we found 2 lines. Passing the silver atoms through inhomogeneous magnetic field. got two lines. Now they were so confident about their properties, but this must be correct. You get two lines. And German students can sometimes be not arrogant, but telling their things very in a determined fashion. Do you know? I'm ठीक है. Then so it made people think. Then there were guys who were back in bodies. They were also young guys. They were in their 20s. Therefore, I said like. So therefore, these stories are more important for people like. They thought that maybe like you have angular momentum, which is actually orbital angular momentum. You don't say orbital, but it's orbital momentum. So there will be something else, intense, which later on turned out to be the spin angular momentum. So this is also the magnetic moment is proportional to vector s now, spin vector s. So and s, so 2s plus 1 eigenvalue, but little s can have values 0, 1 half, 1, 3 half, including half integral values. So 1 half s equal to 1 half, then 2s is 1, then 2s plus 1 is 2. It looks very simple, but they are very deep ideas and thoughts. And look at the experimentation. So one thing is, whatever you do,